So welcome everyone to the Applied Algebraic Topology Research Network seminar. So the speaker today is Neža Mramor Costa, and the title of her talk is Discrete Morse Theory with an Application to Robot Motion Planning.
So thanks very much for the invitation. Thanks for the introduction, Sarah. I'm sure that some of you have heard some version of this talk already, so I apologize to those if I get really boring. You can, do something else. In the meantime, nobody sees what you're doing in these Zoom lectures, so you're welcome to spend your time productively. Okay, so let me start. So I would like to give a short introduction on discrete Morse theory. I'm sure that most of you know the basics of this, but nevertheless, just to set down the concepts and the terminology and notation, let me do that first. Then I'm going to talk about two variants of discrete Morse theory that I've been working on in the past with some collaborators. The first is parametric discrete Morse theory with an application, and then fiberwise discrete Morse theory, again with the application which is mentioned in the title here. So here's my the contents of this lecture in short, in a nutshell. So let me remind you what is discrete Morse theory. So it's a version of smooth Morse theory, which I'm sure you all know very well. It's a classical topic. But the difference here is that discrete Morse theory is defined on spaces with discrete decompositions, for example, simplicial complexes or CW complexes or so on. So on spaces which we can express as a union, as a discrete union of certain types of cells. So it was introduced by Robin Foreman in the 1990s, and it's become quite popular in the meantime. It turned out that this is, at least in my opinion, a very beautiful theory and extremely useful, and it's actually been applied to many different fields. So one of the benefits of this theory compared to smooth Morse theory is that it's very well, due to the fact that it works on discrete, in a sense, objects, it's very well suited for algorithms and for computer implementations, which is important in data analysis, for example. Okay, so here are some fields where discrete Morse theory has turned out to be useful. So there's a lot of work on homology and persistent homology computation. I'm just mentioning a couple of authors here, and I apologize for everybody that I have not mentioned, because there is really a lot of work going on in this field, and just not enough room for everything here. Okay, so probably persistent homology is the topic in applied topology nowadays, and also this application of discrete Morse theory to homology and persistent homology computation is probably the most important type of applications that you can find in the literature now. So there are, of course, also other things. There are some very important applications to combinatorics. Here I would mention Kozlov, then to algebra. Here I'm mentioning a young colleague of mine from Montenegro, which is not so well known, Nela Milosevic, who has done some nice work of applying discrete Morse theory to algebra. Then we have examples of applications to distributed computing by Sergio Razbam and Fernando Benavides, and then to concurrency. So there are very many different fields where this new, well, not so new anymore, but anyway, a relatively new theory has turned out to be very useful. So let me start at the very beginning. So what we're going to have today is a finite regular CW complex. So we start with the zero skeleton, and then we glue on one cells to get the one skeleton, and then we glue on two cells to get the two skeleton, and so on up to the final stage, which is our space X. So it should be a regular CW complex, which means that I've gone a little bit further. I do too much with my hands. I'm sorry about that. And then things tend to jump around. Okay, so it's a regular CW complex, which means that all the attaching maps of cells to the skeleton of the one-dimensional S are embeddings, which means that, yeah, sorry about that too. So this means that the cells in our regular CW complex are homeomorphic to closed disks. So the closed cells, the closures of the open cells are actually homeomorphic to closed disk. This is the context where discrete Morse theory sort of works best. It's not really necessary, but it sort of doesn't do any harm to us right now to restrict to this context. Now, what is a discrete Morse function on F? Well, it's a map which associates a value from the real numbers to every cell in X. So we're going to be dealing with finite complexes, which means that, instead of R, we could use Z, or, well, there will be finitely many values here in play all the time. So to every cell in our complex, we associate a value. So that for each cell, we have one of the three possibilities. So if you look at the function values on this set and on its faces, then at most one of the faces is allowed to have a higher value. At most one of the co-faces of this cell is allowed to have a lower value, or all the faces have lower values and all the co-faces have higher values. Now, if I draw a little picture over here, sorry. For example, if we just take a very simple triangle, so we have three vertices, three edges, and the interior here. For example, we could say that on this vertex, we have the value 0. So on this edge, we can put we have on at most one of the edges, we can put a higher value. So let's decide to put a higher value on both of them. For example, let's say that this is a 1 and this is a 2. And now, since over here on this vertex, we can put a higher value than 2, and then we have this exception here. So on this particular edge, we have this one vertex with a higher value, a face with a higher value, or the other way around. This vertex over here has a co-face with a lower value. Okay, now since this vertex is already an exception, on this other edge, we have to put a higher value, for example, 4, and then over here, let's put a 0 again. And on the top over here, we put a 5. So this is a discrete Morse function, at least I hope, on this very, very, very simple CW complex. So if you take any cell in here, you see that if you compare the values, you see that you have at most one face with a higher value, or at most one co-face with a lower value. So it turns out that only one of these two exceptions is possible. So either a cell has a face with a higher value or a co-face with a lower value. Now the cells were, so this last possibility where the values of the function actually increase with dimension from the faces to the co-faces, these are the critical cells. So here in the C, in this last class, we have these critical cells of the function f. So as I said, concerning the cells which belong to either A or B, it turns out that each cell can belong to at most one. So either A holds or B holds, which means that all these cells, these other cells, are partitioned into regular pairs. So each cell belongs to precisely one, to disjoint pairs, which we can call regular pairs. Okay, so these pairs are usually denoted simply by arrows. So we have a cell of lower dimension, which is connected to a cell of higher dimension. And this arrow over here means that the function values are decreasing. For example, if we look at the picture down here, the edge at the very end would have to have a higher value than the two-dimensional cell to which it's connected with an arrow. Okay, so these arrows sort of denote, connect these pairs, these regular pairs, and they point in the direction from a lower dimensional cell to a higher dimensional cell where the value is decreasing. Now the red things over here are the critical cells. Over here on this edge, let's say that we have the value 1 over here, then we would have to have lower values on both vertices because this cell is critical, and a higher value on the co-face that we have over here. And finally here at the end, we have a critical vertex, which means this would probably be the minimum of the whole function. For example, a -10 would be a good value here. The values on the two edges coming into it would have to be higher. So over here we could put, so this has to be higher than the value here. So maybe this is a -1, maybe this is a -2, but then here the value has to be the smallest possible. Okay, so this is the basic definition of a discrete Morse function. It seems sort of too complicated to be useful, but it turns out that it's just great. Okay, so here's another example. This is a torus. So we have the values given. I'm going to be doing this a lot, I'm sorry. So we have the values given on the cells. So if you look at the values a little bit, you see that the highest possible value is over here in this 2 cell. So this is now a critical cell because all the values on the faces are lower. And then we have these 2 critical edges. So one is this and this identified, of course, and the other one is this and this, because if you look at them, you see the values on the vertices are lower, while the value on the co-faces, so the vertices are here and here, and the co-faces are over here, and everything goes according to dimension. And then the absolute minimum is in the vertex over here, which is now a critical vertex. Okay, now what are these critical cells? They're actually the important, in a certain sense, the important part, because they have a similar role as critical points in smooth Morse theory. So if you look at the critical vertex, then you see, like over here in the picture, we have a critical vertex down here at the edge. Since it's critical, all the values, so over here, the function values go up like this. So these are increasing function values. So from here on, all the function values have to go up along the edges. And then because of the properties also, to a certain extent, up into the sides of these triangles. So this is a local minimum. So a critical vertex is going to be a local minimum of the function. A critical edge has the property that the function values go down towards the vertices and up towards the co-faces, the triangles. So it has the same local configuration as a saddle in smooth Morse theory of index 1. And then if you take a critical cell of maximal dimension, is going to be a local maximum because the function values towards all the faces are going to go down here. So this will be a local maximum. Okay, so I'm looking forward to your questions along the way. Let me know if I forget to say something or if you have any questions, if something is not clear. Okay, so what is the relation to smooth Morse theory? As I said already, a critical cell of dimension I of a discrete Morse function corresponds to a critical point of index I of a smooth Morse function. So the dimension of the cell is really corresponding to the index of the critical cell in the smooth case. So we have this more specific connection between smooth and discrete Morse theory. This is a theorem which was originally proved by Galois in a little more narrow context, and then there was a small mistake in the proof, so Benedetti fixed the proof and prove the theorem, which is stated here now. So the theorem essentially says that if we have a smooth manifold and if it allows a smooth Morse function with a certain number of critical points of index I, so if this Ci is the number of critical points of index I, then we can always find for any triangulation, any PL triangulation, piecewise linear triangulation of M, there exists a discrete Morse function, not on the triangulation, but on a far enough barycentric subdivision. So for some R on the R's barycentric subdivision, we can construct a discrete Morse function, which has precisely the same number of critical cells in each dimension as we have these critical points of the corresponding index. So we see that actually this discrete Morse functions, in particular on triangulated manifolds, actually, due to a certain extent, represent discrete approximations of some smooth Morse functions. Okay, so as I said already, the critical cells are, in a sense, the important part of a discrete Morse function because they're the ones which determine the shape of the space X. So we have this theorem, which is proved by Foreman in the original paper from 1998, which says that if a discrete Morse function on X if f is a discrete Morse function on x, then x has the homotopy type of a CW complex with a cell of dimension I attached for every critical I cell of f. So the proof of this theorem goes in a similar way as the proof of a similar theorem in smooth Morse theory. I won't go into that, but it's not very difficult, so you can find it in many books and other places where discrete Morse theory is considered. So maybe I forgot to mention in the beginning, we have already at least 2 very good books dealing with discrete Morse theory, which I recommend. One of them is by Kevin Knudsen, and the other one is by Nick Scoville. So the field is growing. There are books around, textbooks. So one of the immediate consequences of this theorem is, for example, that we have so since we know that we have this homotopy type of a CW complex, we know that we can compute the cellular homology of this space, which will be determined by the critical by the cells of the complex. And from this, it follows that the number of critical cells in each dimension is bounded by the Betti number in that dimension. So we have the weak Morse inequalities immediately from this theorem. Okay, so these are the critical cells. So the critical cells are the ones which determine the shape of our complex, which tell us what the Betti numbers, which tell us something about the homology of the complex. Okay, what about the regular pairs? So the regular pairs altogether form something which we call the discrete gradient vector field of the function f. And if we look at the connected sequence of these arrows, which, these regular pairs, we obtain something which is called the gradient path. So if we look at our torus example over here, so here's the gradient path that we have, which starts over here on this edge and goes on to this 2 cell, and then it goes maybe to this other 1 cell, and then on to the 2 cell, and here it ends. And here's another one, which also starts in the same place, and then it goes down to this other neighboring 2 cell. So there are many of these gradient paths which crisscross each other. So the gradient paths are complex. If you look at all the set of the gradient paths together, this is a very complex and intertwined object. But one thing which we notice immediately, that if you look at the function values along one of the gradient paths, they have to decrease, because the function values decrease from a cell onto its edges, except if we have an arrow pointing into the cell. And if there is, so if we look at this arrow, for example, we start at the edge over here, and then the function value has to go down from here to here, because this is a pair in our discrete Morse function. Then it has to go down onto this edge, because this 2 cell is already connected to the 1 cell over here. So the function value down here has to go down, and from here we have an arrow and so on. So we see that along the gradient paths, the function values decrease, which is nice because it means that the gradient paths don't form cycles. So this gradient vector field is acyclic. And on the other hand,
Neža, we have a question from the audience.
Yes.
So is it right that the gradient paths between critical vertices are not unique in a typical situation?
The gradient paths between critical vertices, well, if we don't really have gradient paths between critical vertices, because if you have a critical vertex, there is no arrow going out of there. But if you take a gradient path which starts, for example, in a critical edge, then you can go from there to okay, I'm sorry, I'll start again. If you take a critical path which starts in a regular vertex, a gradient path which starts in a regular vertex, like this one over here maybe, then from that, you have only one possible arrow going out. So if you look at these one-dimensional gradient paths, they have this property that they can merge, but they can't split. Okay, so if you take two different vertices, it's not possible to find two different gradient paths between them because of this special property of one-dimensional gradient paths. If you look at higher dimensions, then it's possible for many different gradient paths to go from one critical object from one object to another object. So they're by far not unique, except again in the higher dimension, the highest possible dimension, we have again this special property that the gradient paths can split, but they can't merge because of the geometry which is behind it. Okay, does this answer the question?
Neža, can I also ask a clarifying question?
Sure, go ahead.
So just to get the intuition right about following the arrows. So to move from a low dimensional simplex to a high dimensional simplex, you follow the arrows, but to go down, you don't need an arrow but you can't go backwards along an arrow.
No, to go down, you just go to any face of the object which is not connected to this object with an arrow, because you have this property. Discrete Morse functions essentially respect dimension, they decrease with dimension, except you have this one possible exception on every cell. Okay, so if you look at a cell, for example, this one over here, okay, since it's connected with an arrow to this edge over here, if you look at all the other edges, the function values from here has to go down, okay, because this is the basic property. The function values respect dimension, except you have this one exception allowed for every cell.
I see. So is there this is just like a notational reason. Could you think of there being small arrows going from the high dimensional cell to the co-faces, or is there a reason not to think of it that way?
Yeah, you could do that. You could put the cells down in here, and then all these, I mean, the arrows, and then all these arrows would denote decreasing function values. Of course, you could do that. You could say, okay, function values go down like this and down to here and down to here. Okay, you could use arrows all along.
Okay, that helps clear up the intuition. Thank you.
You're welcome. Any other question? Okay, so as I said, these gradient paths in dimension 1 have the special property that they can't split, because if you have a vertex, you can have only one arrow going out of it, okay? You can't have two arrows going out of this vertex because it's because of these properties. And so these paths can't split, but of course they can merge, because you can have two arrows coming in from different directions to a certain vertex. For example, like over here, you have these two arrows coming in to this vertex. So this collection of gradient paths is quite a complex, really complicated object. If you start, thinking about them, you see that they can do all sorts of things. Okay, can I continue? Okay, so here too, so I'm of course keeping a lot of really basic stuff about discrete Morse functions, because there's no time to go into everything. But here are two facts which will be important for us later on. One of them is that if you have a gradient path of x which starts in a regular pair, so if you have a gradient path which goes sort of like this, it starts in a regular pair, going down like this, and then it goes on, and so on. And then maybe it ends in a critical edge, or maybe not, it doesn't really matter. But if you have this situation, then this, and if this this edge where the path starts is a free face, okay, so it's not the face of anything else, any other cell in our complex, then we can start a sequence of elementary collapses. So we can just eliminate this pair, the edge and the two cell from the complex. We can just perform a homotopy equivalence which squeezes the pair, the edge and the interior onto the remaining boundary of this two cell. And speaking in terms of the discrete discrete decomposition of our X, this just means that we're throwing away the edge and the two cell. Okay, so in general, if we have this situation, if we have a gradient path that starts in a free face, then we can just perform a sequence of elementary collapses along this gradient path. And the resulting complex that we get in the end will, of course, be homotopy equivalent to the original ones. So this gradient path starting in a free phase allow us to simplify our complex in the sense of keeping the homotopy type the same, but getting rid of superfluous cells. We can just perform all these elementary collapses down. Is that okay? Okay, so this is one thing which, one fact which we'll use later on. So another fact, which is really a special case of this one, is that if you have a discrete Morse function with only one critical cell, okay, so we have a discrete Morse function on a simplicial complex or on some kind of a complex which has only one critical cell, then this critical cell has to be a vertex, because remember, everything is finite. We have to have finitely many values. So there's a absolute minimum someplace. So this vertex V, this unique critical cell, if it exists, of course, is going to be the global minimum of the function. Okay, so if we have a discrete Morse function with only one critical cell, then this cell has to be a vertex where the global minimum of the function appears, and everything else collapses onto V. Because in this situation, the maximum of the function has to be on a free face of the complex, okay? If you look at the function values, how they increase from the vertex V, you see that the maximum value, well, it can't be on a cell of maximal dimension of the highest possible dimension, because then that would be a critical cell. So it has to be on a free face. This maximal, this cell with the maximal value has to have an arrow going down from it, which means that we can start a elementary collapse from here, and then we can just collapse from there on all the time, and in the end we're just left with this one critical vertex. So in this situation, the whole complex collapses onto this one point, this vertex where the global minimum of the function is. Okay. Any questions? Okay, this is really not very difficult to see. Maybe, it's quite an easy result. Okay, so this is what I wanted to mention about discrete Morse functions in general. So here are a few words about applications to data analysis. So as I already said in the beginning, at the moment, the most well-known and the most numerous application to data analysis is homology and persistent homology computation, because as we know, persistent homology is one of the tools of computational topology that is really, really used now in machine learning and well, all over the place anyway in data analysis. So in homology and persistent homology computation, we have a number of really efficient algorithms and implementations which are based on discrete Morse theory. So there's a lot of computational topology libraries where the homology computation really rests on discrete Morse theory, because this turns out to be a really efficient way of doing it. I won't go into the specific library, so I'll just leave it there, but it's not difficult to find it. We have the Goody library from Uli Bauer and the Chomb library from Konstantin Mishaiko and other people. So there are a lot of these libraries around. Okay, so this is one application of discrete Morse theory to data analysis, which is really important at the moment, homology and persistent homology computation. So there's another point of view of discrete Morse theory, which is also really useful in data analysis. And this is an analyzing sampled data. What I mean by that is that we're given a function on the vertices of our CW complex, which we can imagine as sampling a function on a certain domain, which is modeled by X. So we have a domain modeled by our CW complex, and now we're measuring some quantity on this domain, whatever it is, I don't know, temperature or whatever physical or other quantity, which is interesting to us, but we're sampling it as it in the vertices of this CW complex. So we reconstructed the domain so that the sampling points are the vertices of our reconstruction. Now, in order to use discrete Morse theory in this situation, well, we would like to answer questions like, how does this function behave on the whole domain where it's defined? We just have the sampled values. How does it behave in general? What can we say about this data set that we have, these measurements that we have? And in order to use discrete Morse theory in this situation, we have to, first of all, extend the function values on the vertices to a discrete Morse function on X. So this is the first step that we have to do, extending these sampled values to a discrete Morse function on X. So there are several algorithms around for that, but of course my favorite one is one that we came up with together with Henry King and Kevin Knudsen. I think this is a mistake, I'm sorry. It should be an O. Sorry, Kevin, if you're around. This particular algorithm that we came up with is a recursive algorithm which produces a subdivision of X into these three classes A, B, and C. The arrowheads A, the arrow tails B, and the critical cells C. These are the ABC cases that I talked about in the beginning. And then, of course, we need a pairing which, describes the specific arrows. So this is a pairing which associates an arrow tail to its arrowhead. So the algorithm is recursive. It runs through all the vertices and it looks at the lower link of that vertex, which means the part of the link of the vertex where the function values on all the vertices are smaller. So if we have a vertex over here like that, and then we have its link, then okay, so here's the link. So we just take the part of the link where the function values are smaller. For example, let's say that this is this and this vertex, maybe, and this one over here has smaller values. So our lower link, so here's the third color to cover all this, the green one. So our lower link now will be this specific vertex over here, and then this subcomplex of the link over here. Okay, so we look at the lower link, and we have this. If we have this subdivision already constructed on the lower link, then we just extend it to the cone over this lower link, so to this part, like this. So it's extended from the lower link to a part of the star of the specific vertex where the function values the function values on all the other vertices are lower. And it turns out that it's a nice algorithm. Oh, and then of course we have to do local optimizations because the algorithm as it is might give us too many critical cells. And so we get rid of all the superfluous critical cells using a very simple a tool which is available in discrete Morse theory. And this is this. If you have, so it's called canceling critical cells. If you take a gradient path which starts in a critical simplex, so a gradient path which starts at the end of in the boundary of a critical simplex of higher dimension and goes down like this towards a critical simplex of one dimension less, then what you can do is simply turn around all the arrows along this gradient path. So just pair this one critical edge, in our case over here, with this critical 2 cell, and then go all the way along the critical path and the gradient path and turn around all the arrows. And this means that you're getting rid of the first and the last critical cell in your gradient path. But you can only do this if these 2 cells are connected by only one gradient path. So allowed if there is only one gradient path. Connecting these two cells. Otherwise, you can't do that because you're going to produce a cycle, and we don't want to have cycles in our gradient paths. Okay, so this very simple mechanism for getting rid of superfluous critical cells is really, really efficient. So what we do is at every stage, whenever we extend our discrete Morse function from the lower link up higher, we get rid of all the superfluous critical cells. And then this gives us a pretty nice discrete Morse function with not too many critical cells. So I forgot to mention over here when I was talking about homology computation, what we really want to have is discrete Morse functions with few critical cells, because then the computations will be less, the complexity of the computations will be smaller due to that. Okay, so we have an algorithm which allows us to extend the values of the function which are given on the vertices to the remaining components of our CW complex. So what does this tell us? What can we do with this now with the discrete Morse function, or at least with its gradient vector field? What does it tell us about the data? So we can think of things in this way. The critical cells represent features in the data. For example, and the gradient paths encode the gradient flow. For example, if you look at this example of geographical data, this is really an artificial example, but you can see that we can also find natural data similar to this one. So the features would be like the local maxima, the saddles. So these are described by the critical cells and the local minima down here. Of course, the local maxima are represented by cells of highest dimension. So this is not going to be a point, but it's going to be a highest dimensional cell. The saddles will be represented by one-dimensional cells, and the minima are going to be actually vertices. So these are going to be the features which are given by the critical cells. Now the gradient paths describe the gradient flow in a similar way as in the case of the smooth Morse functions. So if we have a gradient path going down like this from here, then we know that the function values along this gradient path are going to go down. So this is like the gradient flow is given by the gradient paths. So this is a domain with boundary where the situation is a little bit different. So the gradient paths can also end in the boundary, of course. Now, one thing that you can reconstruct from that are the ascending and descending regions of this Morse gradient vector field that we have. So we can sort of reconstruct what part of the function of the flow, the gradient flow, where the gradient flow goes down, and we can reconstruct this Morse-Male decomposition, which we know from smooth Morse theory. Okay, any questions? Okay, well, here's another example of an application of discrete Morse theory to data. So this is very, there are a lot of examples of image analysis using discrete Morse theory, and of course also other tools for computational topology. So this is a nice picture which is meant for a little break. So this is a picture of a beautiful mountain in the Julian Alps in Slovenia, which you're all invited to visit as soon as this is possible. At the moment, I don't know if you can come to Slovenia because the traveling restrictions, but when you can, come and check it out. It's very pretty. Okay, so how do we use discrete Morse theory for image analysis? Here's a beautiful image, and so what are the features in here? If we do, if we do look at this as a digital image, we know that images, grayscale images, come with a natural cubical decomposition into pixels. So what we do is we look at the dual cubical complex where the vertices are in the pixels. So we have these grayscale values given in the vertices of the complex. So here this black net in here represents the dual decomposition with vertices in the pixels. So we have these values in the pixels, which we then extend to a discrete Morse function on the whole cubical complex. Now, what will this tell us about when we find the critical cells of this? We know that the critical vertices will represent, these are the minima of the grayscale function. So these will be the black domains over here. The critical edges will be the saddle. So these are the bridges between the black domains, like over here, we're going to have a critical edge, which is a bridge between these two and the two white domains over here. And the maximum are going to be the white patches in our image. So if we would go back and try to reconstruct this image over here, we're going to get a lot of critical elements in it, but they will sort of tell us how the light is distributed in this image, where we have the bright parts, where we have the dark parts, and where we have these bridges between the two domains, the dark and the bright domains. So this is actually more useful than it seems on my Slovenian mountain. It turns out that we have actually applications of this to medical images and material sciences. So I think there's a hand raised. There's a question.
Hello. Sorry, I have a question about your previous slides. We have a version, a generalization of Morse theory to Morse bot theory, which instead of isolated critical points, we have isolated critical submanifolds.
Yes.
I guess there is a combinatorial version for this too, in which between these critical submanifolds, I mean, first of all, in a smooth case, between the critical submanifolds, we consider the gradient-like vector fields, like before in Morse theory. And I think in the combinatorial case, we also have a similar thing that between these collections of critical simplices, we have gradient combinatorial vector fits. So my question is, in Morse bot theory, there are approaches that people compute homology groups directly. I mean, instead of perturbing the Morse bot function, they talk about more to a Morse function. They talk about Morse bot function and the critical manifolds directly and compute the boundary operator based on these flow lines between these critical manifolds. Is there any, I mean, people do this in a smooth case because generally symmetric perturbing a Morse bot function make us lose the symmetry in our structure. And this is the reason that they do this in the smooth case. But in the discrete case, I don't know if there is any application or reason that people really like to have Morse, like a combinatorial version for Morse bot theory to consider this collection of simplices instead of one single simplex. Have you seen anything, or do you consider, do you imagine, is there any application for such a thing in a combinatorial setting? Thank you very much.
Sure. I must admit that I don't know the answer to that question. I do know that we were considering, in particular, in image analysis, you have this problem that the critical cells sort of sometimes are not really sufficient to describe the image well. Why? Because there are certain regions in the image where the grayscale value is pretty much the same. I'm talking about the images because this is where we have been thinking about it and doing work. So the idea that we had, and which is sort of natural in the discrete case, is that you sort of merge cells with similar values and consider those as one big cell. So instead of taking your original decomposition, you just merge things together and take bigger chunks of your decomposition together and then work on those. Okay, so take this as your decomposition of the space and work with a discrete Morse function on that, or at least a discrete gradient field on that. I'm not sure if this corresponds to what you were talking about, the critical manifolds. And I don't know about a discrete version of Morse bot theory yet. So thanks very much for the question.
Thank you. Thank you. So this merging, just a quick question, this merging simplices together means what would happen to the gradient flows, the gradient passes between the simplices that you merge?
So what you do is, you really just merge things where the function values are very, very similar. So where the difference is only, like a perturbation, like a small error maybe or something. And then you just declare that the function value is the same on that. And this whole thing is now one cell and you ignore anything which is going on with gradient paths in there. So this is just one big cell now. And we're just looking at what is the remaining part of the gradient field going out of that. Of course, this is not quite the same because the cells are not manifolds. Of course, it's a more, specific situation. So thanks for the question. It looks like an interesting thing to look into. Thank you.
Thank you very much. Thank you.
Okay. So here's the first generalization of discrete Morse theory that we worked with together with Henry King and Kevin Knudsen. So this was a rather old story, which took some time to be, which was published only recently in 2017. So the idea here is that we have a sequence, a sequence of data, which is going through a set of continuous deformations. We'd like to track what is going on with the features in this data. Okay, so more specifically, we have a finite family of discrete Morse functions on one space X. And then we would like to see, so we consider this family F of this family Ft, as t goes from 0 to n, as a sequence of deformations of a specific function. So some process is going on. So this function is changing from together with time, or maybe along, maybe this describes a sequence of slices in a three-dimensional object, or something is going on, and we have a continuous process which changes our function. So we have this finite family of discrete Morse functions on a specific space, on a specific complex X. And now what is the parametric discrete Morse function in this case? So first of all, we define this really, really simple CW complex, which consists of a bunch of vertices and the edges connecting them. So let's say this is 0, 1, and so on up to n. Now a parametric discrete Morse function over this simplicial complex from 0 to n is going to be a discrete Morse function, which is really an extension of this family of functions given on X. So it's a discrete Morse function on the product X times this simplicial complex here. So we have all these slices which correspond to X above all these points, and also above the edges in between. Okay, so we're forming this bigger, higher dimensional thing over here. Okay, so on each of these slices, we have a discrete Morse function. And now we're forming a discrete Morse function on the whole thing, which has the property, what we would like to do is decrease as t decreases. So the function values will typically decrease in this direction. Okay, so this f has to have the property that its restriction to a specific fiber over one of these division points over here is going to coincide with the given function f sub t. And as I said, f decreases with respect to t. So the values on this slice over here are going to be smaller than the values down here. So now we have to sort of pair these things together. So we have all these pairings in the different slices, which are given already. And now to extend this to the whole product, what we do is we pair, so all these regular pairs are already paired in the different slices. The only thing that is left for pairing are the critical cells in the individual slices. And what we do is we pair the critical cells. For example, if there's a critical cell over here, we're going to pair it with this product cell. So this critical cell over here is going to be paired with this product cell, this higher dimension, this product of this cell with the interval from t-1 to t. So we just put an arrow in here like this, which means that all the critical cells will be paired downwards towards the initial stage of our process at time t is equal to 0. So the only remaining critical cells will be over here. Everything will be paired off either within the slices or along the slices as we go on. Okay, so what is this good for? This tells us that we can now connect the critical cells, which are features in our data, which represent for us the features in the data, along these time slices. How? So we take a critical cell in one slice, and so we have a critical cell in the slice over here. And if we look at the neighboring slice down here, maybe, so this is going to be paired like this. Maybe this is regular. Maybe this in the slice over here, it is paired to something, maybe this way over here. But here we have all these gradient paths which travel along the part in between. And we go along all these possible gradient paths until we meet a critical cell down here, okay? At the moment we meet a critical cell down here, we're going to pair it. So this is paired to this one because there's a gradient path going from here along this interior part to this critical cell over here. Okay, so if you look at the picture here, so here we have a sequence of CT scans of the head, and we're looking at the local minima, so like the voids in the skull. So so there's sort of, the notation is not very good, I'm sorry, because the pictures are too small. But if you look at the picture over here, you can see that the critical cell, the critical vertex which appeared over here in the next slice is paired to the same one, but then at some further slice it might be paired to two. So over here maybe this will be paired to two different things. So the result that we get in the end is a bifurcation diagram for the critical cells, which tells us how these features in the data are connected along our continuous process. Okay, so I personally think that this is really cool. So I hope you like it too. So the result is something which tells us how the features in the data behave along this continuous process. This can be either a process in time, like a movie maybe, or it can be a process in space. So maybe it's a sequence of slices, like over here in the case of these head scans, or maybe it can also be something higher dimensional, of course. Okay, so this was parameterized discrete Morse theory. So another generalization of this discrete Morse theory that we talked about is fiberwise discrete Morse theory. This sort of goes in the opposite direction. So over here, we have a product of two CW complexes, and we define a fiberwise discrete Morse function is going to be, so we have a projection. So a projection which goes, for example, onto the first factor, or it might go onto a section S of X, where S goes from X to X times Y is a section. So it could be more general. We have a projection from the product to a section of the first factor in the product. As we will see later, this is what is interesting in our robot motion planning algorithm. So I'm running out of time, so maybe I should really skip a part of this and only talk about the motion planning part. So what we actually do here is we take we take the product of, so we take a robot, which is a mechanical device, and we look at its configuration space. So what is that? This is the space of the parameters which determine the shape, the position of this robot. For example, if you take this really simple case of a robot arm, which is attached with a revolving link so that it can turn all the way around like this, and then you have another arm which is attached to it with another revolving link which goes all the way like this. So you have this simple device with the configuration space a torus, because this arm can form a full angle and the other one can too. So in this case, X is going to be S1 cross S1, for example, like in this case over here. So the question now is, how do we move a point, how do we move our mechanical device, our robot, from one point to another point in the space where it's operating? Well, such a move really represents a path in the configuration space. And as we would like to have a path which, now a motion planner is an algorithm which constructs such a path from any pair XY in our configuration space. So if we take this X is the configuration space. Okay, here we are. If X is the configuration space, then a motion planner is an algorithm which moves the device from an initial position to a final position. And how do we represent this? So we have an algorithm which takes any pair X prime and associates to it a path in the path space P of X, such that its beginning is going to be X and its ending point is going to be X prime. Now, we would like to have a motion planner which is continuous in the sense that it's robust with respect to the initial and the final point. If these are perturbed a little bit, the path won't change too much. Now, unfortunately, we have the theorem of Farber, which tells us that this is possible only if the configuration space is contractible, which is usually not true. And due to that, this was the motivation for the definition of topological complexity, which is the minimal number of subsets of the product X by X, such that we have a continuous motion planner on each one of these subsets. Now, these subsets are called the local domains, and we want to have a continuous thing on each one of them. So our motion planner will really be subdivided into n algorithms. So if we're in here, we're going to use the first one. If we're in the UN, if our pair is in the last local domain, we're going to use the last algorithm. So we have to subdivide our algorithm into a finite number of continuous algorithms which work on only a part of the a certain subset of the pairs X prime. Okay, so I don't want to stretch my time too much, so I'm just going to finish by saying that in the setting of fiberwise discrete Morse theory, we can come up with an algorithm which constructs these local domains, and not only that, it also gives a path for any pair of points X and X prime in our product, which brings one point to the other. So it's an algorithm which provides only the local domains, not only the local domains, but also for any pair of cells in our, well, of course, we have to have a subdivision of the configuration space to work with discrete Morse theory. So for any pair of cells in the subdivision, we can find a sequence of collapses onto the diagonal, which is going to provide a path in the configuration space, configuration space from one point to the other point. So not only do we have these local domains, but we also have an algorithm for coming up with the paths between any pair of points. So I'm not saying that this is the best possible algorithm. On the contrary, there are many, many very good algorithms in robot motion planning, but it is one which is in a way, rests on topology and on topological considerations from that point of view. It's sort of nice for us topologists. So thanks very much. And I'm open for any questions, please.
Yeah, so thank you so much again. Before we take questions, I would like to ask everyone to unmute themselves and clap.
Thank you very much.
Okay, and now it's time for questions.
I wanted to ask a question which is related to Brady Morse theory. So,
Yes.
this is, I think of this as a version of discrete Morse theory that can also work for sort of infinite simplicial complexes. So I was curious if you have any comments on Brady Morse theory, or if it relates to these fiberwise or sort of time varying settings.
So you mean this PL version of Morse theory, which was defined by Bestvina? Do you mean this one? Okay, this
I think so.
Yeah, it's really, really nice. It's just another way of discretizing discrete Morse theory, which in a way is really, really natural too. So I'm not aware of a fiberwise version of that one. I wouldn't be able to answer that question. So I know that there's this essential initial theory that he has, which, as I said, is really, really nice. It's sort of a PL theory, so it doesn't work with the cells, but it works with the triangulation. It's a PL version of.
Oh, I see. So you need a simplicial complex and maybe a more general simplicial complex, but you can't do it with a CW complex. Got it.
I think not, as far as I know, no.
Which makes it harder to use for your product situation, where you're crossing with time, for example.
Yeah, because you have to work with these, what are they called, simplicial complexes instead of just simplicial. It's a lot of, notational problems that turn out.
Thanks, and thanks for the very nice talk.
Thank you.
Okay, thank you. So I will stop the recording here because it's already noon Eastern time, but feel free to ask more questions. It's like once I do that.